Okay, hello and welcome back. So we're moving on to chapter 19. This is the final chapter in the book. We've got 6 sections that comprises our next 2 weeks. But I know you've all had a lot of actually introduction with this because of kind of the way the homework has been structured. And in many ways with the heat equation, with the Schrodinger equation, it's really hard to avoid some sort of Fourier, like series Fourier theory before you get into what it actually means to be a Fourier series or describing Fourier theory, just because of the natural way we might try to solve some of these equations. I'm going to head over to the whiteboard really quick here and just describe the overarching idea here, because I think this will set us up really well for really the rest of the semester. So the overarching idea for Fourier analysis, this is maybe the more technical term, analysis, is that we can extend the property of an orthonormal basis. Recall ONB means orthonormal basis. E sub n equals 1 to d in some d-dimensional space. And the property is, right, in a finite vector space, and we covered this in our homework, that you can write any vector in a vector space as a sum of inner products of that vector against the basis vectors and then multiplied by the basis vectors. And what I didn't quite cover in our homework is that actually this individually is the projection, it should be a J, onto the En direction. So that's the projection of V onto the En direction, but if you add up all D of your projections in a D-dimensional space, that's like me saying, to get to the center of a basketball court from a corner, you can either walk halfway along the edge and then halfway into the center, or you can take the direct vector from the corner into the center. So adding up 2 projections onto orthogonal directions actually recovers the original vector you're looking for, or in D dimensions, adding up D projections onto orthogonal directions recovers the entire vector. Now what's really cool is that this property is not unique to finite dimensions. So I'll say this, to infinite dimensions. In fact, the troubling thing is not this property in infinite dimensions. The hard part in infinite dimensions is finding an infinite orthonormal basis, right? It's constructing kind of this set, which for now I'm going to call E sub n, going from, let's just start at 1 and go to infinity. You can index this a few ways, but let's just start at 1 going to infinity. The hard part is finding an orthonormal basis, which is infinitely large. But we still have the property, retain property, that may be a function, right? Because we want to think about functions as just infinite dimensional vectors. We retain this property where if we add infinitely many projections, we actually recover our original function. And it's not uncommon for this to be referred to as a Fourier series. So a Fourier series. But what we're going to be talking about in the rest of this course is a very specific Fourier series, which a lot of people will refer to as the Fourier series. There's a very specific, very easily obtainable infinite orthonormal basis, which you use to construct the most generic Fourier series. But in reality, every time we're talking about a Fourier series, we're really just talking about this property right here. You have some infinite orthonormal basis, and you can represent a function using its projections. These are kind of the coefficients, using its projections in each basis direction. And then if you add infinitely many up, you recover the original function. So let's clear that and head back to where we're going. We start with the Laplace operator, negative d squared dx squared. And a couple lectures ago, I proved to you all that the spectrum of this Laplace operator was purely real. And I did that by way of showing that the operator was self-adjoint, right? So it's self-adjoint, in particular on this, with these boundary conditions, which I said was natural maybe when you were dealing with the Schrodinger equation particle in a box. So these boundary conditions are natural. This operator is actually self-adjoint within that context, which means that the spectrum is purely real. Spectrum, recall, this word just means the eigenvalues. So the eigenvalues are purely real. And actually, more importantly, another part of that theorem, once we proved it was self-adjoint, we not only got purely real eigenvalues, but we also got and an orthonormal basis of eigenvectors, which in this case is eigenfunctions, right? Because the derivative operator is an operator on functions. And so all of a sudden, jumping back to, hey, how can we find an infinite orthonormal basis for which we could construct the Fourier series? It's right here. We're going to take that operator. We know that its spectrum is purely real, and we're going to use the orthonormal basis of eigenvectors and functions to construct a series. And so I'm going to scroll down a long ways because that's just jumping through a lot of hoops to get here. We know that these are the eigenvectors or eigenfunctions. So these are the infinitely many, and this is for choices of omega equals 2 pi n over L. For specifically those choices of omega, we have infinitely many eigenvectors, which happen to be orthonormal, forming an orthonormal basis. So what does this look like? There's omega equaling 2n pi over L. So what does this look like as an orthonormal basis is our functions look like the following, where the sum on the right-hand side, we can make this a little bit more clear, the a sub n is the inner product of f with sine 2n pi x divided by L, and b sub n is the same, but now we have cosine. It's the inner product of f with cosine 2 pi n x over L. And this is because of what I was describing right away at the beginning, is that this is always how we construct a Fourier series. This is just the most generic Fourier series. This is the one that everybody tries to use because it's a very useful Fourier series. So maybe I would pause the screen right there and make sure you write this down with those specific inner products, just so you know what the Fourier series is that we're referring to. That should be a star in the sense of complex conjugate. Yes, and I guess something that's slightly more important is that this is we need a square root of 2. So the earlier series was missing a square root of 2. So if you wrote that down, make sure you include a square root of 2 on each of these terms. Okay, so let's actually just run one example. It's going to be a bit shorter of a video today, but we'll run one example of this. And let's say, hey, let's find the Fourier series for this function. This function is 0 to the left of L over 2, and it's 1 to the right of L over 2. And I'm going to head over to the whiteboard for this. Construct the L to 0 to L Fourier series for the function f of x piecewise 0 below L over 2, and it's 1 above L over 2. And so all we need to do is, we already know that f looks like this. It looks like the inner product of f with root 2 cosine 2 pi n x over L, root 2 cosine 2 pi n x over L, plus the sum inner product f with root 2 sine 2 pi n x over L, root 2 sine 2 pi n x over L. And this n goes from 1 to infinity. This one actually goes from 0 to infinity. And the reason why we don't have to include 0 on the right here is that sine of 0 is 0. So that would disappear. Okay, so that means that to construct the Fourier series, all I need to know is this, and all I need to know is this. So if I want to find those two values, let's actually calculate this out. This is the integral from 0 to L. F, now keep in mind what F looks like. F is 0 when x is less than L over 2, and x is 1 when x is greater than L over 2. So actually this integral from 0 to L is only turned on once we reach L over 2, which means the integral actually occurs from L over 2 to L, and I have 1 times root 2 cosine 2 pi n x over L dx, and I can compute this integral just by u substitution on that term. I'm going to recover L root 2 over 2 pi n cosine 2, sorry, not cosine, it's going to be sine. The antiderivative of cosine is sine, 2 pi n x over L, evaluated at the bounds, L over 2 and L. And this is going to give me, if I simplify what's on the left there, I'm going to get L divided by root 2 pi n sine at 2 pi n L over L minus sine at pi n L over L. I canceled a 2 there. And if I simplify this a little bit farther, I'm getting L over root 2 pi n. And then over here, this is 0 because that's going to be full rotations of the unit circle. This is going to also be 0 because that's going to be half rotations of the unit circle. And sine is 0, both at full and half rotations of the unit circle. And so I end up with 0 here. So in fact, all of these terms are 0. And now I just have to compute this as well. So switching colors to compute that one. That's going to be the integral from L over 2 to L of root 2 sine 2 pi n over L, there's an x here, dx. Playing the same song and dance, I'm going to recover everything the same, except I'll get a negative cosine there instead. So now I'll have L over root 2 pi n negative cosine 2 pi n x over L, evaluated at my bounds. And this is going to give me L over root 2 pi n negative cosine 2 pi n plus, because it's minus minus cosine, cosine pi n. And if I think a little bit critically about these numbers, 2 pi n is a full rotation of the unit circle, so this will always be 1, and because of the negative sign, there's always a negative there. Cosine pi n is a half rotation. By itself would be negative 1, but when I have n half rotations, I have n powers of negative 1, because a half rotation is going to flip between negative and positive 1 over and over again. And so if I simplify this, this simplifies to L times negative 1 to the n minus 1, all divided by root 2 pi n. And so this, in green, is my inner product in front of the sine terms. I'm going to clear the screen and then rewrite that down. Okay, so let's reconstruct the full Fourier series for f. Jumping back, we remember all of the cosine terms were 0, and the sine terms we decided were negative 1 to the n minus 1 divided by n pi. This is because actually our inner product of f with whatever we wanted on the other side, I never wrote down. They have to have a 1 divided by L in front of them. I'm going to call that G. And on the previous slide, I wasn't calculating this 1 divided by L, so really the coefficients should have been divided by L. So we lose the L in the numerator, and then there was a root 2 in the denominator, but there's also a root 2 in front of sine, so I'm letting those cancel. And I have sine 2 pi n x divided by L. And then I also have the a0 term here, because I didn't actually calculate my a0 term in the previous setting. The a0 term is always calculated separately. That's always going to be just the total integral of f dx, which in this case is the integral from L over 2 to L dx, which the area under that curve is just L over 2. And with a 1 over L out front, this gives me 1/2 for a0. So we want to make sure that we add 1/2 at the end. So there is my Fourier series for this particular function f. Let's jump back to the book and see if I did everything correctly. So looking at the book, you can see they calculate a0 first. Don't forget the 1 over L is in front of the integrals. There's the terms in front of cosine. They're all equal to 0. And the terms in front of sine, they don't simplify the cosines with a -1 to the n and then -1. But I did. So you can see there we have it. The book agrees with mine as our Fourier series for that f. And the book plots some approximations. You can start to see these should look very similar to everything you've had on your homework when you've been plotting those approximations as well. All right, so that's all I have for today. Thanks for sticking with me. I'll see you in class. Bye.